All right, everyone, welcome back. This example will have rotation in it, okay? In the previous example, I kept it a little bit simple and just had forces, right? No rotation, no torques. This one has both, right? So we'll have three separate second law equations, right? They'll still all be equal to zero, okay? Again, this is chapter 12. So what we have here is a rigid horizontal beam, right? Say a board or plank or whatever. It's resting on two scales that are at the very ends of the beam, right? And so those scales would measure some weight, right? But you can think of it for this problem as they are exerting a force upwards on the ends of that beam, okay? You also have a block of mass capital M located 1/4 of the length from the leftmost edge. And so that has a weight, which will be downwards. And then, of course, the actual weight of the beam itself, right? It's not fixed to the scale. Well, I guess it wouldn't matter if it was, but let's say it's not in this case. It has its own intrinsic weight, right? So lowercase mg. So let's draw a free body diagram, and then I'll show you how to come up with the net torque equation, okay, in this case. So I'm going to do it just below. Let's see. I'm going to try and keep it exactly. Whoop, that's not a straight line at all. Let's go back. Let's try this. Straight line. There we go. All right, I'm going to draw the scale as tiny little triangles here on both ends. So they exert a force I'm going to call F left, right? And then F right, FR. The weight of the block resting on that scale, resting on that beam, again, 1/4 of the way from the leftmost edge. So it has an external force, capital Mg, downwards. And from the very center, I have the weight of the beam itself, lowercase mg. All right, and that's it. And that's it. So from this free body diagram, well, I guess we need to designate positive xl or positive xy, and then remember that positive torque is counterclockwise. Okay? So this is the free body diagram. Let's take this to the next page, and I'll draw some second law equations. Copy. There we go. All right. Let's do it over here. Okay. So, first of all, the net force equations. The x direction, well, there are no horizontal forces, so that's nice. In the y direction, what do we have? Well, we have two forces upwards, so we can say FL plus FR, and then minus the two weights. Okay, all right. Easy part is out of the way. Now, for the torques, the important part about determining the second law equation for torques is that you're free to choose your rotational axis, right? That's kind of the beauty of these problems in chapter 12. Because there is no rotation, you are free to choose a hypothetical point of rotation, okay? So you can choose this point to calculate your torques from. You can choose, well, this point. You can choose the very middle. You can even choose, heck, a point here, right? But to make your lives the easiest, I would highly, very much suggest choosing a point from where a force is applied, right? A point that makes the most sense. So let's start with the leftmost point here, okay? So from that was of length L. Let's do it like this. Let's say that's 0, right? If that's length L. So from the leftmost point, the net torques go as follows. Remember that torque, let me jot that down somewhere. Remember, torque is equal to R cross F. Okay, that's another thing to keep in mind here. R cross F. R being the distance from the rotational axis to where the force is applied, and F is just whatever force is being applied. So, if we choose from this point, remember, right there, what's the R value for FL? It's 0, right? It's 0 because there is no torque when you calculate a torque from the point that the force is being applied, right? R is 0 because that's where the force is applied, right? So we don't have to calculate, or we don't even need to consider FL in our torque equation now, because that's our hypothetical axis location. All three of the other forces, though, would provide a torque, right? And I say would, that's the key word here. Would is a hypothetical torque, right? Really, this problem is not rotating. This beam is not rotating, it's not moving. But get yourself in the frame of mind to think that any of these forces could rotate it, right? Or in the case of this scale on the far right, it would prevent rotation, okay? Even though it actually does not. But hypothetically it would. So that means for mg here, let's do it in red. R is this vector here. That's our, well, that's one of our r's, right? And then the force is mg, downwards. They are 90 degrees apart. So now when we write our first term, we have r cross, well, mg. Because they're 90 degrees apart, we just have sine of 90. So we can really write r times capital mg, sine of 90, okay? That's our first torque. Now, is this a positive or a negative torque? Right? Using your right hand rule, using your right hand, if you put your index finger in the direction of R, your middle finger in the direction of the force, your thumb should point in the direction of the torque, right? Which in this case is into the page. Another way to think about that is that if this force, if mg, were the only force present, so ignoring for a second this weight and that force, if this weight from the block were the only force on the beam, that would cause this beam to, guess what? Fall down, right? Or rotate down, right? In the, in the clockwise direction. And so that's opposite to what we said was positive torque. So that means it's a negative torque, okay? And if you want to, you can even write a negative tau is that way, sure, okay? So again, we have a negative here because this weight, right, that force would hypothetically rotate this beam downwards, or in this case, clockwise, right? About what point? About this point of rotation, okay? So maybe you can see that the weight of the beam itself would do the same thing, right? Its radius vector, its r vector now, in red, is now this value, right? Its weight in blue is down that way. They're still 90 degrees apart, and this weight, right, the weight of the beam would hypothetically rotate it clockwise, down, right? It would fall down, basically. So that means the second torque term, whoops, I'm still in red. The second torque term is negative, oh, you know what? I guess I could go ahead and put in what the R's are. R's are. This I should put is L over 4, right? Going back real quick, L over 4, I probably should have written that in our original free body diagram. Okay, so that's L over 4 way. The beam itself is L over 2 from the left edge. All right, so let's go ahead and do that. That is L over 2. Okay, now we can go ahead and write L over 4, and for the second torque, L over 2. mg sine of 90. Okay, and now for the third and last torque term in this equation, we have the force of the right scale. Okay, so that's pushing upwards. That's providing a force like that, up. It's preventing a clockwise motion. So in essence, it's creating a counterclockwise torque, right? It's preventing a clockwise torque. That means it's creating a clockwise torque, right? Another way to think of that is if this were the only force on it, right, it would cause a rotation, whoops, I'm off the screen, counterclockwise, that direction. So that means we have positive, what's that, R distance? Well, that's the entire length of the beam. So that's of magnitude L times the force, which is Fr, and then again, sine 90. But this time it's positive, okay? And normally that would be equal to I alpha, but now it's equal to 0, all right? All right, so we have all three of our second law equations. We have 1, 2, and 3, right? Really we have 2, but all 3, okay? So what do we want to find? Probably should have mentioned that. What do the scales read, right? Right here, which basically means what are FL and FR, okay? What are FL and FR? Well, let's see. In the y direction, we have both of those unknowns. In the torque equation, hey, look at that. What happens there? We can really cancel out the magnitude of L, and Fr is the only force in that equation, right? So we could just go ahead and solve for Fr straight away. All right, so that goes away, that goes away, that goes away. Sine 90 is 1, right? So I'm going to solve for Fr. And that gives us a positive 1/4 capital Mg, sine 90 is 1 again, plus 1/2 lowercase mg times 1, right? And again, I'm just solving for Fr, meaning I brought this to the other side and this term to the other side as well, okay? And once you plug in the values, because we know the mass, we know G, you should get, for Fr, 15.45 newtons. 15.45. Now that we know Fr, we can plug that into the y equation and solve for FL, right? So bringing the terms, these three terms to the other side, we get capital Mg plus lowercase mg minus Fr, okay? And for this, we should get a value of, where is it, 28.7. Okay, now do these numbers make sense, right? Should FL be bigger, right? Almost twice as great as Fr? Well, where's that block located? That block is located right here, right? So it's closer to the left scale, which means that this left scale is trying to prevent, right, or compensate for more mass, right, more gravitational force, because this block is closer to it than the right side is. If this block were exactly centered halfway, both scales would read the same thing, right? But since the block is closer to the left scale is trying to push back against more force, and thus FL is larger. Okay, so I hope this has given you a good, way to solve equations with both no linear acceleration as well as no angular acceleration, right? In the next video, I'll do this exact same analysis, right? However, I'm not going to choose this point of rotation. I'll choose a different point and show you that it comes out to be the exact same value. Okay? Thanks for watching.